In functional analysis, we sometimes encounter operators that act erratically, appearing discontinuous. But what if the overall geometric structure of that operator, its graph, is perfectly closed and hole-free? Can a seemingly wild operator actually be mathematically well-behaved? To answer that, we need three tools. First, Banach spaces, meaning our vector spaces are complete and have no missing limit points. Second, bounded operators, where the outputs do not explode to infinity relative to the inputs. And third, the bounded inverse theorem. Let's look at this 3D coordinate system. We can visualize our input space, x, as the horizontal floor, and our target space, y, as the vertical axis. We measure distance in this combined product space simply by adding the lengths of the x and y components. Now, take an input x and its output tx. If they are plotted together as a single coordinate in this 3D grid, and we let x move across the floor, that point traces out a surface. This surface is the graph of the operator. When we treat the input and output as a single geometric shape, we create a way to inspect the operator's behavior through its structure. This allows us to investigate the relationship between the domain and the range as a unified surface. We're looking at data points sliding along the translucent graph surface. To formally define a closed operator, we track this sequence toward a limit point. If the sequence converges, that limit point must actually belong to the surface, locking right in. The target y exactly equals the operator applied to x. This split screen shows a critical distinction. On the left, a continuous operator guarantees any sequence reaches a predictable target. On the right, a closed operator makes a weaker promise. A sequence might diverge, but if it lands exactly on the target. Take differentiation. Uniform convergence forces derivatives to converge to the exact derivative of the limit. The operator is perfectly closed, yet differentiation is famously unbounded. Oscillating functions can have tiny values, but massive, steep slopes. An operator can maintain a rigid closed graph while producing infinite outputs. Closedness guarantees structural integrity, but not bounded continuous behavior. The closed graph theorem states, if an operator acts between two complete Banach spaces and has a closed graph, it is automatically bounded. As you can see with this surface hovering over the domain, the parent spaces x and y are complete. The product space, the graph, and the domain are hole-free sets. The proof begins with a projection mapping, dropping a point on the graph straight down to input x on the floor. Vector arrows show this downward projection is strictly bounded. Length x is less than or equal to x plus tx. Because every point maps to a unique input, this projection is bijective. We define an inverse map, reversing the arrow to push x back up to the surface. Since spaces are complete, the bounded inverse theorem dictates this upward projection is also bounded. This forms a structural box, meaning the vertical output axis is entirely constrained by the horizontal input scale. Because that upward projection is bounded, the outputs of the operators cannot blow up to infinity. We've proven continuity entirely through geometric structure. We can also flip this logic using lemma 4.13-5. If an operator is bounded, what does that dictate about its graph and domain? This flowchart maps the relationships. First, if an operator is bounded, and its domain is a closed set, those two properties automatically force the graph to be closed. Expanding on that, if the operator is bounded, its graph is closed, and we know our target space y is complete. Those three conditions guarantee that the domain must be closed. As these nodes slide together, we see how the properties lock into place. In complete spaces, a closed domain, a bounded operator, and a closed graph are functionally linked. Identifying any two of these properties provides the structural bridge needed to determine the third. Emphasizing structural completeness provides us with a visual guarantee of functional stability. With the closed graph theorem mastered, we are prepared to apply these principles of convergence to the Banach fixed point theorem next.